Bro, I hate that the physical textbook is these pages.
Okay, so welcome back everyone. Last time we started talking about moles and molecules and atomic mass unit and so on. And we started temperature, or we got to temperature, but we didn't quite continue that. We talked about temperature scales, I believe, the Kelvin versus the degree Celsius. We said degree Celsius is concerned with water, freezes at 0, boils at 100, and then you have your scale based on it. Okay? So temperature scales, let's just quickly review that. Scales. So we said the Kelvin scale, TK, is whatever the temperature is in degrees Celsius, and you add 273.15. So 273. Okay. And then we said there is the Fahrenheit scale, and it was 9/5 of the temperature in degrees Celsius plus 32. And you can go back and forth between all of these scales. Can you tell me if my memory is failing me, or that's where we stopped? Actually, okay, good. Then we said, how do we make a temperature scale or a thermometer, something that measures temperature? And I think we said, look for something whose properties, some physical properties depend on temperature. And one of those things is that objects, they expand when you heat them, when you change their temperature. So if you increase the temperature, they tend to expand. And that got us to linear expansion, and we will have also volume expansion. So if you heat something, if it's one-dimensional, like this, it will mostly extend length. But obviously the area will also expand this way and this way. So there will be volume expansion. The volume will be overall bigger, but it's mostly pronounced as length, as it's volume. But if you have a bulk, like a pot of water or gasoline or something, and you warm it up, it will expand a little bit volume. Okay? So how does the expansion work? So let me write this almost. Expansion. There is linear if it's mostly length. Here is length L. And so suppose I have a rod of length L, and the temperature is T initial. I increase the temperature of the rod, so the rod gets slightly longer. Okay? And you have to do this experimentally. So here's rod, but now it's a slightly longer rod. It's longer by this much. At delta L. And this is T final. The change in length, the increase in length in this case, happens to be, so think about it. If I have two rods back to back, and each of them increases by a centimeter. Oh, here they are, meter sticks. So suppose I have a meter stick. I warm it up, and the length of this meter stick increases by 1 centimeter. Let's just suppose that. Well, let's say I have 2 meter sticks next to each other now. I warm them up. By how much would their length increase? Assuming the change in temperature is the same as before. Yeah, each of them will increase by 1 centimeter, so overall 2 centimeters. So the increase in length is proportional to the original length. So the longer the original length is, the longer the expansion will be. So if I have 3 meter sticks, and so it would be by 3 centimeters in that case. So it's proportional to the original length, whatever it was. Also, changing the temperature by 1 degree Celsius versus 2 degrees versus 3, which one will expand it more? 3, right? So the more the change, after all, why is it expanding? Because of the change in temperature. So it expands linearly with the change in temperature. So this is the change in temperature. Not just the temperature, but the change of temperature. The temperature has to change for this to happen. Now, do you think wood, if I warm up wood by 5 degrees Celsius versus warming up steel by 5 degrees Celsius, will they behave the same way? Will they? No. So I need something that tells me that depends on the material itself, and that's alpha. This is the coefficient of linear expansion. The change in length obviously is length. It has units of length, so in the SI units it would be meters. Length is in meters. Change in temperature. What units do you think we use? Kelvin, or actually degrees Celsius, both work. Why? The temperature in Kelvin versus the temperature in degrees Celsius, they're not the same. But the change of 1 degree Celsius is equal to a change of 1 Kelvin, right? The change, how do you get Kelvin from degrees Celsius? You add 273. So you will add 273 to the initial temperature, you add 273 to the to the final temperature, but the change, you subtract them from each other, so the 273 cancels anyways. So a change of 1 degree Celsius is a change of 1 Kelvin. So in here, if you really want to play safe, and you don't remember, okay, use Kelvin. But it really, it's a change, so a change in degrees Celsius or a change in Kelvin is the same. Okay. And alpha will have what units? Well, I want meters on the left. I have meters here, so meters, tens of meters. I have dimensionless quantity here. This is degrees Celsius or Kelvin. So this one needs to be inverse degrees Celsius or Kelvin. So it's we have units of degrees Celsius, 1 over degrees Celsius, so degrees Celsius to the -1. And this is the coefficient of thermal expansion, linear thermal expansion. That's the coefficient. So let me write down just a couple of materials. Just a couple. Here is alpha for aluminum, and then alpha for steel. And alpha for aluminum is 2.4 times 10 to the -5. And you can find them in different tables. 2.4 times 10 to the -5 degrees Celsius to the -1st power. And for steel, it's 1.2 times 10 to the -5 degrees Celsius. So which one expands more readily, steel or aluminum? Aluminum has a larger alpha, so it will expand. So for the same change in temperature, in fact, aluminum will be twice the change. It will expand quite twice. Okay. Quick example, and then we will go to the coefficient of volume expansion, and then go from there. Okay. So here's the example. Suppose you have a steel pipe, and it's 55 meters long, and it's a cold winter day. So this is the pipe, and it is 55 meters long. So L is 55 meters long. And the temperature is 5 degrees Celsius. And then the pipe, you turn on the faucet, or you turn on, they say here it's an oil pipe, let's say, and hot oil runs through it, and it happens to have a temperature of 155 degrees Celsius. So it will expand. The temperature finally is 155 degrees Celsius. Okay? And so the pipe gets longer by a delta. And it's a steel pipe. And the question is, what's delta L? In this case, I think it's straightforward. Just apply this. We have alpha. It's steel, so we just look it up. And it's listed here, so just write it down. Delta L. Alpha and delta T. The change in temperature is 155 minus 5, so that's 150. Okay, so this happens to be approximately 9.9 centimeters. 5.9 centimeters. So 55 meters is long, it's like 160 feet or so. But 9.9 centimeters, it's not that much, but it's like this, right? About 4 inches or so. Yeah. So you get that. Next, the coefficient of volume expansion. The idea is you have a volume. It's L this way, L this way, and L this way. So when you heat it, it's going to expand. It will expand in all directions by a little bit, right? By a delta L in each direction. So the new volume would be L plus delta L cubed, right? So we'll worry about that in a second. So you have, it says delta V, the change in volume, is equal to the original volume times the change in temperature times the coefficient of volume expansion, or volume thermal expansion. That's beta. This one is the volume expansion, that one is linear expansion, right? Alpha was linear, and this one is the volume. But what would the units of beta be? Same as alpha, yeah. Because volume, they cancel, so you must have dimension this here, degrees Celsius. So this one must have 1 over degrees Celsius, or 1 over Kelvin. So yeah, the units would still be, for this one, they are degrees Celsius minus first power. Let me give you some betas here. Beta for aluminum and beta for steel. Just to compare the two, just to compare these. So for aluminum, beta happens to be 7.2 times 10 to the minus 5 degrees Celsius to the minus first power, and this one is 3.6 times 10 to the minus 5 per degree Celsius. Not 50. How do they compare? Let's start with steel. Beta compared to alpha. Huh? Yeah. Seems like 3 times, right? Beta for the aluminum compared to alpha. Also looks 3 times. It's approximately, yeah, it's approximately 3 times. 3 times as much. And you can see that by doing geometry and expanding the cubic, or we can do it this way. Let's notice that beta is about 3 times alpha. Beta is about 3 times alpha. Let me show you why that's the case. So notice here, what's the volume? Yeah, the volume is L cubed, right? You have a cube, right? Volume is L cubed. Now, dV is equal to dV dL dL. What is dV dL? What's the derivative dV dL?
Yeah.
Yeah, that's, we don't need the parentheses anymore. Yeah, there. So I want to work, let me just write the next one. That's correct. Yeah. So by thermal expansion for the volume, dV, small increase in volume, dV would be beta V dt. Beta V dt. This one is a finite change. If it's an infinitesimal change, I would call it dV. So dV is beta V dt. So that's right. So this one is just beta V. here I have 3L squared times dl. But dl is alpha L dt. Delta L or dl is alpha L dt. Let's compare. I can before I cancel anything, let me put here beta. The volume is L cubed, right? dt. Here I have 3 times alpha times L squared times L is L cubed, and then dt. L cubed, L cubed. So I get this, beta times dt equals 3 alpha times dt. How do they compare? Beta is so yeah. Sounds good. We're going to continue. As I mentioned, the topics are a little bit scattered. You get gases and you get liquids and solids, and we talk about temperature, we talk about ideal gas processes. So it's a little scattered, but in a chapter or two we'll be more focused. I would mention here phase changes. By the way, any questions on this before I go on? Yeah. Okay. Yeah. So think about it. Mathematically, dV is the same as dV dl dl. Yeah, you can do it. Yeah. And the advantage is, okay, I have a dl on the right, and dV dl gives me dl squared, which allows me to relate dV to dl. Because how do you define like the differential dy in calculus? Definition of dy is dy dx. Okay, so phase changes. Different phases. We said you got the, for example, you have ice. You warm it up. What do you get afterwards? What happens to the ice? It starts to melt. So that's melting. So it goes from solid to liquid. It melts. But if I freeze the water, if I put the water in the freezer, it will go from liquid to ice. It goes from liquid to solid, and that's freezing. So you get melting versus freezing. Okay. Now, if you take that water, put it in a pot on the stove, and keep heating it. After a few minutes, it will start to what? Boil and you get some water vapor. So in that case, you had boiling, right? And if you cool the vapor, it will condense and become liquid again. So that's condensing. So boiling versus condensing. That's all I wanted to mention about those. We'll come back to it. We'll do calorimetry. How much heat we need to add to do this to cause certain changes. Or we do this, I give you this much heat, or this much heat is added to something, and then what's the final state of the object.
So can we use this relationship with phase changes?
Or this one?
If we wanted to describe liquid water to vapor.
For this relationship here?
Yeah.
No. No, this one is just property for just expansion. It doesn't change phase. Solid just expands, stays solid. Or liquid expands, stays liquid. So the next thing is ideal gases. Ideal gases is the next topic. And by the way, this expansion, you can use it to make a thermometer. And I have an example in the worksheet that we did last time. I don't think I finished that example. Do you want to go over that example or continue with this? Continue? Do the example? Okay, sure. Let me put that because I don't have the number. I don't remember the numbers, but the idea is simple. Suppose I have like something that has this shape. So it has a lot of, let's say alcohol or something here, or mercury. We're trying to make a thermometer. And this is neg, and it has a diameter. The diameter here is B. And it's filled with, let's pretend it's maybe alcohol. And I will use two different colors. So it's filled here. And the volume is 815 cubic millimeters. And the temperature here temperature is 25 degrees Celsius. But when you put it in something warmer, let's say you warm it up to 26 degrees Celsius, what happens to the level of that fluid? It will go up, right? It will expand with the thermal expansion. It will go up. And it gets to this level. T here is 26 degrees Celsius. And the reason it goes up and you can visually see it is because a small change in volume here will be more pronounced in length there because the pipe here is narrow. It's narrow. It's narrow so you can see the length easily. So, and then let's say the height is 1 millimeter. Say the height increases by 1 millimeter. Let's suppose also this material has a beta of 750 times 10 to the minus 6. Okay. That's big for this material. And the question is, find the diameter. Find the diameter. So I would right, this is expansion. It's volume expansion. And the volume expansion is it says the following: delta V is equal to beta times the volume times the change in temperature. Beta is 750 times 10 minus 6 per degree Celsius. Volume here is 815. Cubic millimeters, I need to change it to cubic meters. What do I do? Multiply by what factor? 10 to what power? It's -3 or -6 or -9. Yeah, because cubic millimeters is millimeters times millimeters times millimeters. You have to do it 3 times. Each time it's 10 to the minus 3. So yeah, so it's 10 to the minus 9. The change in temperature, what's the change? 1 degree Celsius. That's just 1. That's on the right side. On the left side, we want to relate the change in volume to the diameter. Well, let's magnify it. Let's look at the geometry of this segment, this one here. Let's magnify it. It looks like this. This is H, and this is the area. So delta V is the area times the height. But the area is pi r squared, right? The radius of this, and then times the height. But the radius is half the diameter. And then, so this becomes 1/4 pi diameter squared times h. That's the change in volume there. That's the increase of volume. Yes, you agree? Cylinder has a volume of pi r squared times the height, or the area times the height. This one is in meters because it was 815 millimeters, so I changed it to meters. Yeah, all the numbers are in SI units, okay? The ones I got. And then, yeah, so the change in volume here, I'm going to write 1/4, and then pi, and then the diameter squared, and then the height. Let's ask. The height is 1 millimeter, so I want to write it in SI units, which is meters. So I want, how many meters is it? 1 times 10 to 1 power. Minus 3. So 10 to the minus 3. 10 to the minus 3. And I don't want to spend too much time with the numbers. So you divide, take the square root, and you get the diameter. So I'm going to just say the diameter is going to be 0.00082 meters, which is 0.882 millimeters. That's the diameter. So it's a thin pipe, a thin tube. On purpose, it has to be very thin so that a small change in volume will show as a long length or an appreciable height that you can see with your eyes. Yeah, so 750, it happens to be ethanol, by the way. The one that has that data, it's ethanol. Okay, we're going to talk about ideal gases. And whatever I'm going to state about ideal gases will be developed more and more. And ideal gases will stick with us throughout our journey with thermodynamics. They will go away when we get to electromagnetism, but for now they will stay. So ideal gases, an ideal gas is a gas of non-interacting atoms. So you've got atoms, they are moving around, but they don't interact with each other. They don't attract, they don't repel each other. It's a simplification, but it's a useful one. Okay. In practice, if you have a real gas like oxygen or nitrogen or something like that, or helium, if it's dilute, if there are very few of them, it comes really close and it behaves like an ideal gas. Okay. So how do ideal gases behave? Well, they're governed by the following equation. Ideal gases. So let's first of all capture the ideal gas in a container. Basically, that's the container. This is a piston. On the piston. The reason we have a piston is so that our container can get bigger or it can get smaller. So we can make the container smaller or bigger. So notice there is gas here, or gas molecule. And those gas molecules are moving around. They're colliding with the walls, and then sometimes they collide with the piston. Each of them collides. And if there are enough of them, there would be constant collisions, which would be constant, some net force on the piston. And there is the atmospheric pressure. In this case, let's say we're in the atmospheric pressure from the top. So there is a force from the atmosphere downward, and there is the force from the gas molecules upward. And if the piston is in equilibrium, not moving up, not moving down, they're in equilibrium. So it means the force from the bottom will equal to the force from the top, assuming the piston is massless, by the way. Let's assume it's massless. Then we know what the pressure is. Pressure is will just be atmospheric in this case. Right? So the pressure from top equals to the pressure from the bottom. So we can talk about the pressure of the gas. Okay. We can also talk about the volume of the gas. So how do we measure the volume of the gas? How do you find the volume of the container? Well, if it's a nice cylinder, it's the height times the cross-sectional area. If it's more complicated, then you just have to find the volume some other way. But we can find the volume. Okay, so we can talk about the pressure, you know how to measure. We can talk about the volume, right? Next is we can talk about the temperature of the gas. Assuming somebody made a nice thermometer for us that we can measure with. So we can measure the temperature of the gas. So we can always know what the temperature is. So there is the volume of the gas, the pressure of the gas, the temperature. And then another thing is the number of molecules or the number of moles in there. So somebody got there and counted that maybe. There are more efficient ways, but let's say we know how many moles of gas we have. Maybe we can figure out the mass of it, we know the molar mass, and so we can figure out how many grams or how many moles of gas, right? So we can somehow find that out. The ideal gas law relates all of these quantities. So the ideal gas law says this. If you take the pressure of the gas, multiplied by the volume of the gas, it would be proportional to the temperature and the number of moles that are here is called the ideal gas constant. PV equals to nRT, as many have seen in chemistry, or some of your chemistry lectures. So let's just be elaborate and make sure we know what we're talking about. So P is pressure. And SI units are newtons per square meter, which is a Pascal. Pascal. Volume is, V is volume, and it's in cubic meters. Sometimes it's given in cubic centimeters, sometimes it's in liters, but you always have to, or you might want to change to cubic meters to be on the safe side. Next is N. What do you think little n stands for? Moles. Number of moles. T is the temperature. In Kelvin. Has to be in Kelvin. See here, the temperature is in Kelvin. Because this is not the change in temperature, but it's the temperature. So there's a difference. Because if I say 0 degrees Celsius, are you really going to plug in 0 here? Say nRT equals to 0, so the pressure times the volume are 0, when they are not. So you can say the temperature has to be in Kelvin. Temperature has to be in Kelvin in this case. And again, to be safe, you can always use the temperature in Kelvin. And then what is this R? Is the ideal gas constant or the reversal gas constant. Ideal gas constant, all right. And it has a value, it's a constant. It can be measured. It's 8.314 approximately. I like 4 sig figs, 8.314 joules per mole times Kelvin. That's the ideal gas. Now, another way you can see another form of this ideal gas law, you might see it in the following form. That's PV equals to N KB. In fact, let me work with this one, show you how you can modify this into the form that I want. The number of moles, how do you get them? Well, if you know the number of particles and you divide them by Avogadro's number, it gives you the number of moles. Remember? If you have the number of particles equals to Avogadro's number, that's 1 mole. If the number of particles is twice Avogadro's number, that's 2 moles. So the number of moles, little n, is just the total number of particles divided by Avogadro's number, and then here I have my RT. Let's regroup them. We will write the number of particles and then R divided by Avogadro's number, times the temperature T. This R over NA is called KB. So N times KB times T. So this KB R by Avogadro's number, 6.022 times 10 to the 23. Divide that. So you have 8.314 divided by Avogadro's number. What do you get? I'll wait. 8.314 divided by 6.022 times 10 to the 23. All in the denominator. Yeah. That's good. Yeah, it is. It's 1.381 times 10 to the minus 23. In this case, for this one, we joules per Kelvin. So we got here some one of the moles. So you can have it as into it's approximately 1.38. I think it's 0.65, but usually for sig figs 1.381. And this constant here is called Boltzmann's constant. And it has this value. It's also constant. So which ideal gas law form do you use? Both of them. Both are equivalent to each other. One divided on by this. This one to me is more transparent because it just tells you the total number of molecules. This one is a little bit less because I know the number of moles. But they're the same. They're equal to each other. And so for this one, the advantage of this is R is a small number, right? It's a number, it's 8. 8 you can count in one or two hands. And little n, the number of moles, is also you usually have a few moles, right? 1 or 2 or 3 moles. And you have a few moles times R, which is 8. So 4, 5, 6 times 8, you're talking about 10. So a number that this product is usually in the tens, right? On the other hand, here, Boltzmann's constant is a really tiny number, 10 to the minus 23. But the number of molecules or particles is large or small?
Small.
The number of particles.
Large.
Large. You have a lot of oxygen molecules in this room. So yeah, this would be large. So you can take an extremely large number times an extremely small number, and then you get their product would be a moderately large number, a moderate number that's 10 or 15 or 20 or something like that. So for this one, you have two moderate numbers multiplied to get another moderate number. For these, extremely large times extremely small. Okay. All right. Let's do an example on this ideal gas law. How am I doing? I mean, erase the board.